So, last time we introduced the course and we introduced, well, we reviewed a lot. That's one thing we did. We reviewed a lot. And then we talked about lines, how to solve for x. We talked about elimination method for solving systems of linear equations. We talked about, oh gosh, what did we talk about? It seemed like we talked about it all, but we really got it going. We got it started, okay? So what we'll start with is kind of what we ended with was elimination method, okay? I know that the homework is due tonight. The quizzes are due tonight. So if you're still working, that's understandable. But I'm just going to plow ahead because we have a bunch of things to cover for this week. And this week is harder than last week. So I need to explain as much as possible within the time I'm given. So that's what I'm going to do. I'm also most likely going to use the calculator for various things more than I did last week because there's a lot of arithmetic that we need to get through as opposed to spending our time and energy on that. We need to understand kind of the bigger picture. So I'll probably use my calculator more than I used last time. So if I get frustrated with the computer about the calculator, please excuse me. But yeah, so we have a lot to go over, but we're gonna really dive into this idea of system of linear equations, and then we're gonna expand that idea into matrix algebra. So that's kind of where we're gonna end, is the idea of matrix algebra. And over, since the last time I talked to everyone, one thing that I've been reading about was all the Apple released, or I guess they just released a video of their VR goggles. And so the internet's all excited about VR again. So I was kind of thinking about, well, what math would they have to do with all of that? And really, that's what we're learning. So just to try to give you a premise of what we're talking about, why this might be important for technology or for real reasons other than business. Of course, you can use this for business purposes, but for any LCD screen, any screen, you could think of it as a matrix of pixels that have usually 3 colors. So they would have an amount of red, green, or blue, I think it is. And so you could think of that as a matrix. So if you have thousands and thousands of these pixels, that's what's displaying the screen. But then you would also have a location of items, and those locations of items would be listed as their coordinates, and that can be listed as a vector, or that can be listed as a matrix. And then transformations, so things as they scale. Like for instance, if you're watching me on the computer screen, I'm not actually that size. There's only one person that sees me in real life right now, but how that scales, the ratio, that can be scaled through transformations. So like Instagram filters, for instance. Everything is within ratio to the other, but you could make things larger or smaller, or you could make things different colors within one another, and all of those would be matrix transformations. So all of that is exactly what we're learning. Okay? But when this was developed, it was just thought of as pure math. It's come to fruition being extremely practical math. Okay? Anyway, so that's maybe what you could use this for. You can also use it for business purposes, but mostly what I'll focus on is how to do it. Okay, so I'm going to flip through sections 2A and 2B and try to explain the lesson while looking at the homework. Okay, that's the idea. Okay, so my annotation tool works. Yeah, good going. So here it says, write the system of linear, excuse me. Okay, Write the solution of linear systems corresponding to the reduced augmented matrix. So they're saying this is already reduced, and we want to write the linear system. So we looked at something like this before. Let's look at it again. They're using x1, x2, x3. We could think of it as x, y, z. Either way, x1 minus 3x3 equals 7, and x2 plus x3 equals -6. It says select the correct choice below if necessary and fill in the answer boxes complete. There's a unique solution, there's infinitely many solutions, there's no solution. And what I want to call your attention to is this row of zeros right here. This row of zeros pretty much solidifies that we will either have no solution or infinite solutions, because we have 3 variables and only 2 rows. Okay, to have a unique solution, we need at least as many rows as variables. And here we only have, what's happened is this is reduced away. So now we only have 2 rows for 2 variables. Right? So at best, we're going to have infinitely many solutions. We will not find a unique solution. So it could be no solution at all, or it could be infinitely many solutions. And I believe this is going to be infinitely many solutions. Okay, we will look at in a moment, or maybe in a few moments, we'll look at a matrix that has no solution. But I think this one has infinitely many solutions. And what I'm going to do is it says have x3 be the free variable, which is t. Let it be t. All right. So if I let that be t, then I can write this as x1 minus 3t equals 7, and x2 plus t equals -6. And I want to solve for x1, solve for x2. So by doing that, x1 must equal 7 plus 3t, x2 must equal -6 minus t. See if that's true. So those are lines. Those are infinitely many solutions to this problem. And that's happening because the last row is reducing away. It's reducing away. So we would need at least 3 rows to have a unique solution where x1 equals this number, x2 equals this number, x3 equals this number. But this, we have infinitely many solutions. We have x3 being the free variable. That's usually what we do. We allow the third variable to be the free variable. So these both turn into lines. So that's how I would think about that. That's why that's happening. That's why that's occurring. It might feel a little confusing because they just gave us the result. So we're starting with the result after they've reduced their matrix. So after they've reduced their matrix, this is what they're given, and we're just finding the solution. Well, the solution is infinitely many solutions. I'll save a picture of that, and I'm going to move on to number 2. This is very similar. Use row operations to change the matrix to reduced form. Okay, so it's almost, it kind of feels like it's almost done, but I just need to finish it. And what am I looking for? What I'm looking for with this type of problem is I want this to turn into something like 1, 0, 0, 0, 1, 0, 0, 0, 1. And then this will be some number, this will be some number, and this will be some number. And then I'll have a solution to this system. That would be a unique solution. So ideally, I could reduce this, and it would become something like that. That's my goal. Okay, so how am I going to do that? That's what I want to do. How am I going to do that? Well, the only thing that's in my way right now is this column. I need to fix that column. Everything else is fine. I need to fix this column. So I need to turn the 3 into a 1. I need to turn that 6 into a 0 and that -5 into a 0. Those are the procedures I need to do to make this correct. So that's what I'm going to do. How do I do it? The way I'm going to do that is I'm just going to say 1/3 row 3 becomes row 3. If I do that, then the third, that 3 in the third row would just become 1. That will become my pivot. And then I can adjust this. So 1 0 0 0 1 0. Haven't changed this yet. That's a 1 now. 1 0. And then -9 divided by 3 is -3. Okay, so as I say, we want that -5 to turn into a 0, 6 to turn into 0. How are we going to do it? This is how I'm going to do it. To get that -5 to become a 0, I need to use this 1 here. That's my pivot. So I need to use that 1 in some way. And what I'll do is I'll go 5 times row 3 plus row 1 becomes row 1. That would do it, right? 5 times 1 is 5 plus -5 is 0. So that would do exactly what I needed to happen. Everything on the right side, the augmented side, will just be a consequence. All right, how am I going to get that 6 to turn into a 0? Using that 1 there, I'm going to go -6 row 3 plus row 2 becomes row 2. That would do it. -6 times 1 is -6 plus 6 is 0. So everything would be right on the left-hand side. And then we'll find what these solutions are, okay? All right, so let's do it. We've talked about it, let's do it. 1 0 0 0 1 0 0 0 1, and then that would still be -3. Okay, so let's talk about row 1. That would be, I guess I'll use my vanishing pen. We have 5 times row 3, so that's -15 plus 1, -14. It is. Okay, and then -6 times row 3, it's +18. 18 plus 0 is 18. So I think this is 18. Right. So what the computer wanted me to do was to just enter that information in here. It had boxes for all of those, and I just entered them in. That's all I did. So that's how I would do that by hand. And that is a unique solution. That's what I mean by unique solution. The question doesn't ask about this. I'm going to bring it up anyway. That would be x1 equals -14, x2 equals 18, and x3 equals -3. Or xyz if you're thinking about coordinates. If you're thinking about position. Okay, if you're thinking about position, that would be your xyz, your location. So if you're thinking about a video game or something, the position in the room or in the level, that would be their coordinates. Okay. If we're talking business, then that would be whatever those variables. Maybe it's time and materials, that kind of thing. That's the idea. That's the idea. All right, so I'm going to skip number 3 for right now. I might come back to it. I hope to come back to it. But it depends on how how much time it takes me. 3 can either be, I can either explain it as like a 20-minute problem or a 4-minute problem, and I want to see how much time I have. So I'm going to skip it and then come back. Okay. Basically means I want to see how fast I go, and I'll either use a I'll use a calculator or not use a calculator. That will be. I'll let time decide how that goes. So I'm going to skip to 4, and we'll see what happens. Right? So 4, solve using Gauss-Jordan elimination. That just means we want to do the row operations with our matrices. Okay, that's what we mean. But I already noticed in this that I have 2 rows and 3 variables. So at best, I have infinitely many solutions. At worst, I have no solution at all. So we got to see what happens. So let's see what happens. I'm going to turn, it asked me to use Gauss-Jordan elimination, so that's what we do. And I'll turn this into a matrix. So that's 2, 1, -5, -4, -3, 0, 33, 24. Okay. So as I say, we have 3 variables, 2 rows. So it's either going to be infinite solutions or no solution. Okay. That's the deal. It won't have a unique solution. Okay, so what's the goal here? What am I trying to do? Well, I'm trying to do my operations so I will get something that looks like 1, 0, 0, 1. And at best, I'm going to have some number here, another number, and another number. Okay, so that would be the infinite solution scenario. Okay? But notice, at best, I will never be able to solve for that third column. It'll just be x1 in terms of x3. Because I only have 2 rows, so there's no way for me to limit. So that's what I'm trying to do. All right, let's see if I can do it. Well, I want the first row, first column, that 2 there, I want that to be a 1. And I think I want to do, since they gave me a 1 for free, I'm just going to exchange the rows. So row 1 for row 2. Okay. So they already gave me 1. I'm just going to switch out. They gave it to me for free. So by doing that, I'll just switch the order. 1, -4, 0, 24. It's so easy to get. Even if you've done a million of these problems, which I haven't done a million, they probably have done 1,000. It's really easy to get lost because you're just moving numbers around. So definitely got to watch the bookkeeping and always keep track of what you're doing. So 1, -4, 0, 24. Okay. 2, -5, -3, 33. So I just exchanged the rows and then I got the 1 where I wanted. Okay, so I want that 2 to be a 0. I want that 2 to be a 0. How am I going to do that? I'm going to -2 row 1 plus row 2 becomes row 2. I think that would do it. That would turn that 2 into a 0. -2 times 1 is -2, plus 2 is 0. Okay, it should work. Do that. What happens? First row does not change. So I believe this becomes a 0. Right? Then I have -2 times -4. It's +8 minus 5 is 3. -2 times 0 is 0. Plus -3, -3. -2 times 24 is -48 plus 33. 5, 1, so I think that's -15. still human. I have to sometimes write stuff out. Can't keep it all in my head. Okay, so we're getting close. We're getting close. Now I want this 3 to be a 1. I want that 3 to be a 1. I want this -4 to be a 0. Okay. So I'm going to go 1/3 row 2 becomes row 2. I think that would solve my first problem. Row 1 does not change. That would be 1, -1, -5. Okay. Now, the one where I need it, I need that -4 to turn into a 0. I'm going to use that 1 to my advantage. 4 times row 2 plus row 1 becomes row 1. That should do it. Zero. Okay. 4 times -1 is -4 plus 0 is -4. 4 times 5 is 20, so that's -20 plus, so that should be +4. Hopefully I did my arithmetic. So I think I did what I was supposed to do. I have my 1001. I have -4, -1, 4, -5. Okay, so what does that mean? Let's look at that means -4x. What I can do is I can solve x1 in terms of x3. In terms of x3. And it says, if you do that, use x3 to equal t. Use it to equal t. All right. So if I do that, that would be x1 equals 4 plus 4t. See, that was the solution. Second row. Says x2 minus x3 equals -5. So solving x2 in terms of x3, which they say use t as your free variable, x2 equals -5 plus t. So that's infinitely many solutions. So I think my x1 is 4 plus 4t. My x2 is -5 plus t, or t minus 5. Doesn't matter, either order. And then x3 equals t. So there's infinitely many solutions to this system. That's the idea. Let me ask, am I going too fast, too slow, or just right? A little fast, okay. I think when when there's all this arithmetic, I get a little nervous. I tend to go a little fast. Because imagine being recorded on the internet, doing this. When you do your homework, now imagine doing it in front of people while it's recorded. So I get a little nervous and I tend to go a little fast, but the good thing is it's all being recorded. See? Got it? And it's right. Thankfully I didn't goof up. when I goof up, that's going to be a nightmare. But that's the idea. Okay, so there's infinitely many solutions. All right, well, think about a video game or something and a character, or let's talk about like an enemy, a 3D game. Well, they might be viewing your character. So there's a line going from the enemy to you. There's a line that crosses there. That would be infinitely many solutions. So if they walk that line, they would see your character, or you would see each other. Okay, that's what we're doing. Now, I'm not supposed to be teaching video games. I'm supposed, but it's my summer too. But we can think of this as a business. Okay, well, there's on this line, right? We have profit and revenue. That's what we're thinking of. So as long as you're on this line, we've got a solution. Anything outside of it, there's no solution. We have infinitely many. Sometimes when we look at practical examples, we might see that, well, a person could make that profit and they could infinitely work, right? If we set this up as far as time goes, sometimes you have an infinite, you don't have enough time, we never do, but the time, like if you could somehow work 1,000,000 hours in a week, that would still be on your profit line. That's the idea. So that's why there can be infinite many solutions. Because usually we just have a minimum amount of time. So that can be something that happens as well. So we're finding lines as it's occurring. Okay, so that's infinitely many solutions. And that's using the Gauss-Jordan elimination. Let's look at number 5. Now, number 5 looks terrible, and it looks a lot like number 3. The good news is I did this one before, and I think it's no solution. And so at least we'll be able to see what no solution looks like. So I'm going to convert this linear system, and this is 3 variables. So they must intersect somewhere, surely, or they don't, or maybe there's a point. There is no point where they all intersect. Okay. But here we do have 3 equations and 3 variables. Right. So if I convert this into a matrix, I got 7, 3, 1, 23, 10, 3, 1, 2, -3, 20, -2, and 5. So again, ideally, we will do some row operations, which would cause this to go to 1, 0, 0, 0, 1, 0, 0, 2, 1, some number, some other number. That's what we'd want to occur to find a unique solution. I claim this has no solution, but at the moment, I don't see that. Okay. And when I legitimately did the problem by myself, I didn't know. I just dove in and continued. I didn't see anything that would cause that to happen when I initially started. Okay, so I want that 7 to be a 1, and I noticed that they gave me a free 1 there. So I am personally in favor of going row 1 is exchanged with row 3. That gives me the 1 without introducing fractions at this stage. And I always want to avoid doing fractions and matrices where possible, because it makes the arithmetic much more hairy if I have to do things like 23/7. So I don't want to. All right, so this step, I'm just exchanging. 1, 3, -3, 5, and that's 7, 3, 1, 2, and that's 3, 10, 2, -2. Did I exchange those right? 1, 3, -3, 5, 7, 23, 1, 20. Middle row should not change. Okay. Think I did it. Think. All right. The next step, we want to get rid of that 3 and get rid of that 7. Turn those into zeros. I'm going to turn that 7 into a 0, that 3 into a 0. It's going to turn out that it ends up being row 3 that vanishes. So how do we get rid of these? So to get rid of the 3, we would go -3 row 1 plus row 2 becomes row 2. That's my idea. Everything else would be a consequence, but that would get rid of that 3 there. So -3 plus 3 turns into a 0, and that's what I need. How do I get rid of the 7? We go -7 times row 1 plus row 3 becomes row 3. One, 0, 0. Row 1 doesn't change. Row 2, okay. So that's -3. Let's just work on row 2. So -3 times 3 is -9 plus 10 is 1. -3 times -3 is +9 plus 2 is 11. -3 times 5 is -15. Now row 3. -7 times row 1. So -7 times 3 is -21 plus 23 is 2. -7 times -3, +21, 22. Then -7 times 5, -35, plus 20 would be -15. Any questions so far? It's a lot of steps, but be sure to use your calculator. One thing I notice, it takes a little practice to see this. I see that this and this are multiples of each other. So 1 and 2 and 11 and 22. What's going to happen is that third row is going to zero out. So I mean, it takes some practice to see this. As you can see, these are just multiples of each other, and that's going to zero out. Okay, that's exactly what happens. So when we try to zero out this 2 for the next step, because remember, trying to get this to be a 0, what happens is these numbers are going to go to 0. So let's see that happens. So oops, I'm still in vanishing pen. Okay. So -2 times row 2 plus row 3 becomes row 3. What's going to happen is the left-hand side is going to turn all to zeros. The right-hand side doesn't. That means, well, I'll show you what it means. There's no solution. -2 times 1 is -2 plus 2 is 0. -2 times 11 is -22 plus 22 is 0. Then -2 times -17 is -34, which is not 0. It's not 0. What we've shown here is that 0 equals a number that's not 0. Okay. Whenever these go to all 0, the right-hand side does not, that's confusing. That's very confusing. How can that be? So we've solved that 0 equals 14, and that's impossible. That's a contradiction. Since this is not 0, these are zeros. 0 can only equal 0, right? It can't equal another number. So this is no solution. If this were only 2 variables or only 2 lines, we would see that they are parallel lines. But these are planes where all 3 of the planes, there's no point in which they all intersect. Okay, that's the idea. So for this, there's no solution because there is no point in which those 3 planes all intersect, which means that at least 2 of them must be parallel. So if you ever see that, where the left-hand side all goes to zeros and the right-hand side does not, that means there's no solution because there's no possible way that 0 equals some number other than 0. But if the third line, we saw this in another question, maybe the first one, sorry. Maybe it was the first question. In the first question, the third row was all zeros. That's okay. 0 equals 0. 0 always equals 0. 0 always equals 0. So there's infinitely many solutions. But there's no possible way that 0 equals any other number. So there's no solution to this. And that's what you saw in algebra class when you just had 2 variables, x and y. If you ever saw for where they intersect, the 2 lines intersect. If you had something like 0 equals 2, that's no solution. But now we're in 3 dimensions, so we see it a little bit differently. Okay. But it could also mean that in your business or in the business that you're analyzing, that the boundary conditions are showing that this doesn't exist. There's no solution in which all 3 of these can exist at the same time. That's the idea. That's the idea. So I claim that this is no solution.
Why does option C have x2 equals s? What does that mean?
That would mean that there would be 2 free variables. So that would be the case where that it would be that there's 2 free variables. That can happen in other situations where there are infinitely many solutions and we end up having 2 free variables. So that's what C is referring to, but this is certainly not that case. So we were either going to get a unique solution, and that's what we get in number 3, which we haven't gone over yet, or we get no solution, or we could get infinite solutions with 1 free variable. That could happen, but in this case, we found no solution because one of the rows zeroed out, but the solution didn't. So that's what's going on. If you have something like 4 variables and 3 equations, you would have the opportunity to have 2 free variables. That can happen as well. So we need something other than just t. So you have ST, S and T. That's the idea. All right. I think I wanted to go over 6 as well. Yeah. Because it's a word problem. I always try to go over the word problems for everyone. So in number 6, a chemical manufacturer wants to lease a fleet of 28 railroad tank cars with a combined carry capacity of 528,000 gallons. The tank car with 3 different carry capacities are available: 6,000 gallons, 12,000 gallons, 24,000 gallons. How many of each type tank car should be leased? Let X1 be the number with 6,000, X2 be 12,000, and X3 be 24,000. Select the correct choice below and fill in the answer boxes with your choice. Okay, so we need to come up with hopefully some equations to try to solve this and see what's going on. Now, maybe you remember the jazz ticket question that we talked about last week. That was an important one. It's a little bit like that, but it's getting a little bit more opaque than just those tickets. But that's a really good question, so don't lose track of that one. So here we have an amount of tank cars, and then we also have an amount of gallons. So I think we could set up a gallon equation, and we could set up a tank car equation. I think that's something we could do. So that's what I'm going to try to do. So I think I'd have X1 plus X2 plus X3 equals 28. And then from there, I have my gallon equation. Gallon equation would be 6,000 X1 plus 12,000 X2 plus 24,000 X3 equals how many cars we have. Good question. This was my tank amount. For my jazz tickets, that was the amount of tickets. So that's what I'm thinking. We have like an amount of tickets. And then for the second one, this is gallons. But in the other one, that would be income revenue. So this is my gallon equation. Okay, so we want to try to solve this, but you can see we have 3 variables and 2 equations. 3 variables, 2 equations. So at best, we're either going to have infinite solutions or no solutions. There's no way we're ever going to have a unique solution because we don't have enough boundary conditions. Okay, the first thing I want to do is make my life a little bit easier. I'm going to divide by 1,000 on that second equation and just kind of get into some whole numbers. It seems like that would be at least one thing I could do. And I'll also convert this into matrix because I think I'm supposed to. 1, 1, 1, 28. Just turn that into 6, 12, 24, 5, 8. So there I am, my matrix. Okay. So I at least set it up. So from there, what can we do? Well, we could try to solve this. Also seems like another thing I could do, simplify some of this. 6. Yeah, I think make things even easier for myself, at least with the arithmetic. I could do 1/6, row 2, row 2. It looks like those are all divisible by 6. I could also do that. Fortunately, I'm running out of room though. I'm gonna do the arithmetic. Better. And that's 1, 2 for 88, not 12. Now, let's try to solve this thing. So what do I do? How do I get that 1 to become 0? Well, I could do -1 times row 1 plus row 2. Okay. Negative row 1 plus row 2 becomes row 2. Neat. Zero. 1. 3. 60. Sure. Now, how am I going to get not that one, excuse me. How am I going to get this to turn into a 0? How am I going to do it? Similar, I could do a similar thing where I could say negative row 2 plus row 1 becomes row 1. That would turn that into a 0. Okay. Would be 0. -2. Is 60 plus 28. Did I do that right? I didn't make any arithmetic mistakes. Right, that I did. My brain's getting tired from all the arithmetic. Did I do it up? Does it look right? No, might be right. You see the mistake, let me know. Okay, so what did we get? We got x minus 2x3 equals -32. X2 plus 3x3 equals 60. I think that's what I got. So what does that mean? I can move this over. Yeah, I can move this over to 3. Solve for that. X1, do they want t? Yes. X1 is -32 plus 2t. X2 equals 60 minus 3t. Yeah. Almost there. Okay, now what's going on with this boundary? So you can see what I wrote as the answer. Where on earth did I get that? Because we've never done something like that before. Because these are real items in the real world, not just money, okay? They have to be in a positive amount of things, okay? So you could have 0 of tank car 2, but you can't have a negative amount of tank car 2. Or think of tickets or jazz tickets. For that, you can have 0 of this type of ticket, but you can't have a negative amount of ticket. So I had to solve these, set these greater than or equal to 0. So let's go to red. So if x1 has to be greater than or equal to 1. Oh, sorry, 0. X1 has to be greater than or equal to 0. Has to be positive. Okay, it's a real thing. Right? And we can go into debt. So you can have negative money, but you can't have a negative amount of physical things. Okay, so we need to set that equal to greater than or equal to 0 for X2 greater than or equal to 0. And then solve that inequality. Okay, then you solve that inequality. So here I have negative 32 plus 2t is greater than or equal to 0. And 60 minus 3t is greater than or equal to 0. And that's where I found that t has to be between 16 and 20. Okay, that's how I found that. So these are my inequalities. There. Because they're a physical item. Physical item. Okay, I'll save a picture of that. Hopefully, you can piece that together when you're looking at that problem on your own. So hopefully, in combination, looking at this again, you can put that together. All right, finally, we get to the easy stuff. So the first half of the homework is the hard. Now we're on the easy. Okay. So get ready. Matrix algebra is nearly as easy as regular algebra, especially when we're talking addition. Okay. There's only a few things I need to mention, which really don't even apply to this problem. But you have to have the same dimensions of a matrix to be able to add them or subtract. And these are 2 by 2. That's a 2 by 2, a 2 by 2. So we can add them. They have to be the same dimensions. Okay? These are, so no problem. These are the same dimensions. So you just go 6 plus negative 4. 6 plus negative 4 is positive 2. Negative 6 plus 5, negative 1. 5 plus 3 is 8. We're just adding the entries. 0 plus negative 3, negative 3. We're just adding entry for entry. That's it. That's why they have to be the same dimensions, though. They have to be the same dimensions because we added entry by entry. Right? So if they're not the same dimensions, we can't add them. All right, easy stuff. I hope. So that, just adding those up. Okay. Matrix multiplication is a little bit harder. It's a little bit harder. We have to be careful, and it does take a little practice. I find it to be a bit simpler than even these, 3 by 4 row reducing. I think it's a little bit easier than that. Let's take a look. So we're going to try to multiply these. Okay, we're going to multiply matrices now. Multiply matrices. So this is a 2 by 2 matrix, and this is a 2 by 1. It has 2 rows, 1 column. Okay. So we want to multiply these. How do you multiply a matrix by another matrix? Oh, carefully. That's how you do it. So the first thing I want to show you what your result will look like. This is how I like to think about it. It really helps me keep things straight. So I'm multiplying a 2 by 2 by a 2 by 1. The inner dimensions have to be the same, and of course they are in this example. So the inner dimensions are the same. What it will result as is the outer dimensions. So what we're going to get back is a matrix that's a 2 by 1, which looks, that's the same type as that 3 by 1. Okay. So that's what we're going to get out of this. How do you multiply matrices? I claim that we're going to get just two numbers. Well, it's just going to be one column. Right, this is how you do it. You're going to multiply the first row by the first column. First row by first column. Okay? First row by first column. All right, 9 times 3 is 27. Plus, I'm going to really spell it out, -8 times 1. That's going to be the first entry in that matrix. 27 plus -8 times 1. Now, of course, we're going to combine all that together, but that's how I'm getting what I'm getting. All right, now what about the second row, first column? -1, 1 by 3, 1. Second row, first column. So that's -1 times 3 plus 1 times 1. So let's put those together and see what we get. 27 minus 8 is 19. -1 times 3 is -3. -3 plus 1 is -2. So I think the product of these two matrices is that matrix. That's the idea. Row by column, row by column. That's why the inner dimensions have to be the same. And the outer dimensions is what you're going to get. Outer dimensions is what you get back. That's the idea. Let's keep going. There's plenty more to see. Saved a picture of it. All right, finally, another easy one. We have a number times a matrix. A single number times a matrix. This is called scalar multiplication. I don't think you'll ever be asked what kind of multiplication this is, but that's what it is. It's going to scale this. All right, think of Instagram filters. This could be turning the whole picture a little bit more blue. That's what this would be like. Everything becomes or you could think of brightness, right? When you take a picture on your phone, you can adjust the brightness. This would just be adjusting everything to be a little bit more white or a little bit darker. Okay, that's the idea. So increasing it, decreasing it. This is increasing it by 4 in this example. So that's the idea. Okay. Now, a picture is going to have thousands of pixels information. This, not quite so many. Okay, so we just want to multiply everything by the number 4. Everything by the number 4. Okay, I'll spell it out just so we see what we're getting. That's the idea. And 0 times 4, 0 times 4, -4 times 4, 2 times 4, 0 times 4, 4 times 4. Instead, we have 20, 36, 0, 0, -16, 8, 0, 16. It's just scaling everything up by 4. Scaling everything up by 4. But everything is within ratio of itself. Okay, everything's scaled up. So you can think of just adjusting the brightness of a picture. Everything's 4 times what it was. It's 4 times brighter. That's the idea. So each entry gets multiplied by that number. Another matrix multiplication problem, I think we should do it. You got to practice as much as you possibly can with this stuff. This is a 2 by 2, 2 by 2. So we're going to get a 2 by 2. 2 by 2 is going to come. The inner dimensions are the same. We get the outer dimensions out. Okay. So let's do that. All right. So we're going to get -1 times 9 And then -8 times 7. Sorry, -7. That'll be the first entry. That's row 1, column 1. All right, row 1, column 2. Row 1, column 2 is -1 times -7, 7. -8 times -4 is +32. Second row, first column. 1 times 9, 9. 8 times -7, -56. Then, second row, second column. -7, and 8 times -4, -32. There you have it. Okay, so that's how to do it. I personally always write the dimensions of my matrices. If I just get in the habit, then I always know where I'm going. Let's see what's going to happen. 47, 39, -47. There you go. All right, and then one thing just about the homework, can I mention? That's how to do matrix multiplication, but how do you enter this in? I just want to show this really quickly. So I want to enter in a 2 by 2. I'm doing a similar question. I want to enter a 2 by 2 matrix. If I go down here, you can see that it offers that matrix button. And if you click that matrix button, you can select what size you want. By default, it's asking me 2 by 2. That's what I want. And then I can enter in my entries. That's how I do it. I just wanted to show that because, of course, I'm more worried about teaching you how to multiply matrices, but you should also know how to enter it in. And I had to do a couple steps. So I might negative, oh, sorry, 11 is just more practice. So I'm gonna move on for time reasons. Let's look at this one. This is number 12. And let's look at the dimensions. We have a 1 by 3, a 3 by 1. So a 1 by 3, a 3 by 1. 1 by 3, 3 by 1. The inner dimensions are the same. Great. The outer dimensions is what we get out. What we're going to get out is a single number. We get a single number with something like this. Okay. That's exactly what happens. So we have 7, -4, -1, 1, 2, -3. And so you go row by column. It's 7 -8 +3, and that's -12. Single number out. Just because of the dimensions. But the homework help part of me, I also wanted to mention I had to enter that in as a matrix. The first time I did it, I just entered in -12 because it's just a number. And it said, oh, you're wrong. So I had to enter this in as a matrix here. So if we get a similar question, you can go here and I have to enter in this number as a matrix. So I'll hit the matrix button. And I'm going to go one by one, single one. That's where I entered my -12. So I just wanted to mention that's how I did it and how I entered that in. I'm sure the instructions tell you something like that. I'm going to at least give you a warning because it surprised me. I just entered -12 when I was doing my homework. I was surprised to get it wrong. This one's easy because it doesn't work. That's always good for you, right? Let's look. It wants us to find AB. It wants us to find A times B. Okay. Well, this is a 2 by 3, and this is a 2 by 2. So A by B is 2 by 3, 2 by 2. Uh-oh. The inner dimensions are not equal. So this is not defined. This is not defined to exist, right? If you go into computer programming or whatever, you can redefine this in your computer program, what you mean when this happens. There's different languages that do this, but for our purposes, math theory, that's what we're talking about. Inner dimensions do not equal, so it's not defined, so this is not defined. But you could go B times A, right? That would work, but that's not what it asked. That's not what it asked. So I think that's undefined. This one is basically just what we've been talking about, but just a few more steps. It's just a few more steps. So question 13 or 14? 14. Okay. So with this question, I want to do B plus AD. That's what I'm asked to do. I would suggest multiplying A times D first and then adding B. PEMDAS, right? PEMDAS, it's coming up again. So I'd say multiply first, then do your addition. That's what I'm going to do. So I want to find AD. I see that the option of it not being defined is there. So it's possible, since they randomize it, that some of you will have ones that are undefined. I don't know, but mine was. So I'm going to do that. So this is A, and this is D. And that is a 2 by 3. And that is a 3 by 2. So it's going to output a 2 by 2. And B is a 2 by 2. So it will exist. All right, let's see. Well, do you guys want to see me do it, or do you want me to move on? Guess I'll ask the audience.
Yeah.
You want to see it? Okay, I've got it. All right, so let's do it. So I'm gonna first find AD. Seven, 8, 4, -4, 3, 7. Then D, 7, 2, 5, 3, 0. Then give me a 2 by 2 matrix. -7. Let's do. Oops. First row, first column. 49 plus 16 plus 20. Achieved. 49 plus 16 plus 20. I'm getting 85. Check my arithmetic. That's my dime. first row, second column. Negative 21 plus 0 minus 32, got negative 53. Second row, first column, 28 plus 6 plus 35, got 69. Second row, second column. That's negative 12 plus 0 minus 56, negative 68. So that's me multiplying them. Now I need to add B in there. Add B. B is 8 and negative 7, 6, 4. Hopefully I did my arithmetic correctly. 8 and 85, 93. Negative 7, negative 53, negative 60, 6 and 69, 75, and 4 and negative 68, negative 64. Yep. All right. Here we go. It's a lot of steps. I don't know how many steps. Felt like, say 24 steps. Each one is fairly easy. It's fairly easy to see what we're supposed to do. We're supposed to multiply and add, but it's a lot of arithmetic for sure. Question about that? And I hate arithmetic, even though I'm a math teacher. That's the way it is. Any questions about it? Any more word problems? This is a good one. It says the entries A, B, C, D plus another matrix equals this matrix. Figure out what those entries must be. Could be a little confusing. Let's take a look. All right. So remember with matrix addition, we're just adding entry for entry. Entry for entry. Right? Okay. What does that mean? Well, that means A plus negative 1 equals negative 2. I'm just taking this entry plus this entry equals this entry. That's the idea. And I think from that I can solve for A. And what about B? That says B plus 4 equals negative 6. C plus 0 equals 8. And D plus 1 equals negative 5. One B equals negative 10. C equals 8. D equals negative 6. D, B, C, D. 1, negative 10, 8, negative 6. We have it. Similar idea, except in this one, I'm multiplying. In this one, I'm multiplying. Let's see if I can still solve it. All right, so row by column. row by column. Let's see what happens. 3a minus 3c equals negative 12. Three b minus 3d equals negative 3. Second row, first column, 2a minus c equals negative 4. Second row, second column, 2b minus d equals 1. So that's me multiplying it out. Now I'm supposed to find a, b, and c, d. To find these, how am I going to do that? I noticed when multiplying these out, this is equation with a and c. This is an equation with a and c. Right there. So I have two equations and two unknowns. So that means 3a minus 3c equals negative 12. 2a minus c equals negative 4. I also noticed two equations just dealing with b and d. And say 3b minus 3d equals negative 3. 2b minus 3 equals 1. And the way I did it was I treated this as a system of equations. This is a system of equations. And I just solved. There's two separate ones. You can solve it. Well over on time with the first section. That one, I think there's only one more I need, maybe two more I need to show. All right, this one. Last one, word problem, cost analysis. A company with two different plant manufacturers, guitars and banjos. Its production's cost for each instrument are given in the following matrices. Okay, so we have plant X, guitar and banjo, plant Y, guitar and banjo. And it says find 1/2 of A plus B. Right. That's really all you do. I just added 54 plus 63 and divided by 2. Okay, that's really all I did. Because it said 1/2 of A plus B, add 54, 63, divide by 2. I just entered it to the nearest cent. That's it. 30 plus 40, 70 divided by 2 is 35. That's it. Now, that's the last one. I said I didn't know how number 3 would go for time. I'm glad I didn't go step for step because this one has been taking me around 10 minutes to do. So I'm going to show you the short way. So I'm going to use my graphing calculator to solve this, but you certainly can solve it by hand. It's just many steps. And I need to show at least one with a graphing calculator anyway, so this is perfect. So hopefully I can turn this on. Okay, I got my calculator on. I want to enter this matrix. I want to reduce this matrix. Second matrix. Maybe. No. Edit. make a matrix. And what is this matrix going to be? It's 3 rows, 4 columns. This is 3 by 4. Okay. Enter my entries. 2, 2, 5, 12, 3, 18. I'm just entering it. So far, I just entered in the matrix. So I entered in my matrix A. That's all I've done. So I want the calculator to reduce this for me. I don't want to do it by hand. I've ran out of time. So I'm gonna go to the home screen. So I hit second, and quit. And I go back to the home screen. And now I want to do some matrix math. Second, matrix. And I'm gonna have it do a little math. So I go to math. I want to reduce row echelon 4, which is capital B. It's capital B option. The graphic calculator. Calculator, I want you to reduce that matrix for me. Reduce row echelon 1. Then I'm gonna pick my matrix. Second, matrix. Select matrix A. Hit enter. And it tells me the answer. -5, 4, and 2. You can see that that is the answer. So I am using the graphing calculator to do this. There are 1,000,001 calculators online that will do this for you as well. If you do not have a graphing calculator, you're just doing the homework. You can just Google matrix calculator. You will quickly find a matrix calculator that will do that for you as well. Okay? There is endless amounts. But this particular problem, it takes, I filled, I don't know, 2/3 of a page reducing it by hand. It can be reduced by hand, it's no big deal. But there's your by calculator. Might as well use that too. All right, that is the first half. Are graphic calculators allowed on the final? Yes, they are. Cool. You may use a graphing calculator for your midterm and a graphing calculator for your final exam. So you're allowed to do that. And then it doesn't have to be a graphing calculator to do this. I have a Capsio that doesn't graph, but it still does matrices. So you can, it doesn't necessarily have to be, but a graphing calculator certainly does it. And Texas Instruments TI-83 certainly does it, and all the Texas Instruments above do that. All the newer ones can do matrices as well. Okay, that's the idea. All right, so I'm going to take a 10-minute break now. I'll come back and I'm going to talk about 2B. And we'll talk about more matrix. So I've been recording the lectures and I will continue to do so as long as technology works. And then I'm going to post them as announcements. So when I'm posting them, I have here under the recent announcements, you can see I put recorded video, lecture notes, and more. So that's the recorded video. Here are the lecture notes that I posted. Those are screenshots. I posted those as a zip file because it's a bunch of pictures. So if you're interested, you can download that and then open up the zip file. And then the lecture notes is literally my notes. I just scan them because when I come to class, I have my notes. I have a scanned copy of those. If you're interested, especially when you're, you know, preparing for the midterm or something. And then this is the yesterday or last week's lecture. I chopped up on YouTube. You can chop up what's going on. So I tried to do that. So we went over 1A, so that's the intro. And you have 1A number 1, 2, and so I just chopped up the numbers for the problems that I was working on. So I assume when you go back, you don't want to have to watch the whole video. You might just want to reference one of the problems or a few of the problems. And we can't go over every problem, but I thought that would help. It's a little time consuming on my end, but we only meet once a week as opposed to 4 times a week. So I don't mind doing it. Helps. I will. So I thought that might be helpful. And we go to the YouTube video. I think I noticed I want to show more. That's all the time codes there. You can see that. You can also scroll. So I wanted to look at 1B problem 7. How did I do that? I thought that would be helpful because I assume you don't want to have to watch a whole another 2.5 hours, especially if you suffered through it the first time, but maybe you just want to reference one of the problems we go over in class. So as long as I have time and I'm able to do that, I will continue to do that. Okay. Can't promise it'll all be done within 24 hours, but I'll keep working on it while you keep working on it. Okay. So this very lecture will come out hopefully tonight. I'll get it all uploaded and then I'll try to chop that up as soon as I can. This is how I mentioned. Okay. The homework. So you should be able to see me and you should be able to see my homework. Yeah. Annotations. Here we go. Now for this, what we're going to build up to is matrix algebra. Now, what have we done so far? So far, we've reduced matrices. Maybe the most labor intensive of everything is reducing them. We've talked about how to add them, add matrices as long as they're the same dimension. You can add them, but you're just adding entry for entry. So it's very straightforward. You can subtract matrices. Very simple, entry for entry as long as they're the same dimension. We've talked about multiplying matrices. They have to have inner dimensions are the same. We showed how we're defining matrix multiplication. And then in this homework, in this section, we'll talk about what it means to divide a matrix. Because if we're going to develop an algebra, you need to solve for variables, right? Because how we started this class was say you had something like 2x plus 3 equals, I don't know, right? And you want to solve for x, okay? In algebra class, what did you do? You subtracted the 3 and you divided by 2. Okay, that's how we did it. So you get 7 halves, okay? That's how you would do it in algebra class. What does that mean for matrices? How would you divide by a matrix? If X was a matrix, how would we solve for this? So that's what we're thinking about in this section. Okay, we're all building towards matrix algebra. So the first question, I don't think it actually says it. It says, find the following matrix products. Note that each product can be found mentally without using a calculator or a pencil or paper. So what I want to call your attention to is this diagonal of 1s and everything else is a 0. This is called the identity matrix. And the identity matrix works just like the number 1 in regular real numbers. Okay, multiplying the number 2 times 1 is just 2. 1 times 2 is 2. 2 times 1 is 2. This is the identity matrix, and that's exactly what happens with this matrix. Okay, so if you have 1, 0, 0, 1 times any matrix, you'll get that matrix back. -5, 8, 7, 5. I claim we're going to get that same matrix back. Now remember how we're doing this? Row by column. So that's -5 times plus 0 is. Then 8 plus 5 is 8. So there you have it. Your first, second row, first column, we get 0 plus 7. Second row, second column, we get 0 plus 5. 5. We just get the same matrix back again. Okay, just like multiplying the number 1. This is how the identity matrix works, but you can see for your very self that that's how it works. And multiplying either way with the identity matrix works the very same. So even though this is the identity matrix, which I'll use a capital I to represent the identity matrix, we still get it back. So if this is matrix capital A times I just equals A. Just like in high school or maybe middle school algebra. 1 times A equals A, where A is some real number. It's the very same. You just get it back. But we need the number 1 in this matrix algebra if we're going to develop an algebra. You have to have a number 1 for it to work. And so we define it as the identity matrix. So this says examine the product of 2 matrices to determine if they are the inverses of each other. What on earth does inverse mean? So inverse. Well, what did inverse mean with numbers? 2 and 1/2 are inverses of each other. Okay, 1/2 is inverted 2. Those are inverses of each other. 2 inverse is 1/2. And what does this equal? 1. What about the other way? 1/2 times 2 equals 1. Those are inverses of each other. So in matrix algebra, I need a matrix times another matrix that would equal the identity matrix. That's the idea. And then if you want to see other fractions, you could say 3/4 times 4/3. They're inverses of each other, but they equal 1. But we want the matrix version of that. So you want some matrix times another that equals the identity matrix, which is just a column. It's a diagonal of 1s. Everything else is 0s. Okay. This question asks, are these inverses of each other? So that means when you multiply these 2 matrices together, do you get the identity matrix back? That's what we're asking ourselves. Let me get rid of this stuff. So we want to know, let's call this A, let's call this B. If I multiply these together, do I get the identity matrix out? Where the diagonal is just 1s, everything else is 0. Is that true? Is that what happens? Let's see. -3, 2, -8, 5, 1, -9, -3, 6. Right, I'm going to try and multiply these and see what happens. Row by column. Okay. So that first entry better be a number 1, or these aren't inverses of each other. So -3 times 1 is -3. Plus 2 times -3 is -6. That's not the number 1. And that first entry had to be the number 1. So these are not inverses of each other. So I can tell by the first entry that they're not inverses of each other. From the very first entry, I can tell. How would I know? Well, if I multiply these together, it would have to be 1, 1, 1, 0, 0, 0. Oh, I should be careful because that's not. These are 2 by 2. So it would look like 1, 0, 0, 1. That's what their product would have to look like if they were inverses of each other, which they are not. So that's why I believe they're not inverses of each other. All right, let's take a look at 3. Here it says, examine the product of the two matrices to determine if they're inverses of each other. If they are, we're going to get 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. I found that I didn't get that. Okay. But if they were inverses of each other, that's what it would happen. Okay. I found that that is not the case with these numbers. All right. This one says find the inverse. This one says find the inverse. Now I have to find some matrix M. So they give me matrix M and they say find the inverse. That means M times this other matrix equals I. I have to find that. What matrix times this matrix equals the identity matrix? That's what I'm trying to find. We're going to use the notation for the inverse matrix as a -1 up top. That kind of comes from an algebra thing where you might not think of it, but 2 to the -1st. If you remember exponents, that's what's going on. But that's just a notational thing. That's what they mean. They mean the inverse. So we're looking for what matrix times this matrix equals the identity matrix. This is a 2 by 2 matrix. And when it's 2 by 2 matrix, there's 2 ways we could solve. Well, I guess there's 3 ways. The first way is I'll show you that we can reduce this matrix in a certain way to find the identity matrix and the inverse matrix. The other way is a formula. There's a formula for 2 by 2 matrices. That's another way we can find this. And the third way is we could use a graphing calculator to help us. There's at least 3 ways to do it. Okay, I want to show you first the row reduction way, and then I'll show you the formula. And then probably when we do a 3 by 3, maybe I'll show you the graphing calculator, because those are a little bit hard. All right. I'm going to take the matrix I was given. So far, so good. And on the right-hand side, I'm going to put the identity matrix. That's the idea. So on the right-hand side, I take the identity matrix. So this is matrix M, and this is the identity matrix. And I claim if we row reduce this augmented matrix, we will get the inverse matrix. Okay. So if we row reduce this, we will get the inverse. All right. This is always time consuming, but I think we should at least understand that there's all this different ways, and it's easier with 2 by 2 than 3 by 3. And 4 by 4 is a real thing. Okay. So what do we need? We need the 2 to be a 1 We need that -7 to be a 0. What are we gonna do? Well, I think there's no way out but through. So let's do it. I think it's 1/2 row 1 becomes row 1. Let's just go straight forward. Okay, so from there, I have 1, 7/2, 1/2, 0. And then I haven't changed row 2 yet.
Yeah, the second number in row 2 needs to be 24, not 2. Or sorry, -2.
Goodness, thank you. That could have been trash. Thank you for saying that. It looks like Jack just wrote that too. Yeah, if you ever see me do something like that, please shout it out. Thank you. Okay, so far, other than that correction. So I just multiplied the first row by half. All right, we want to get rid of that -7. So 7 times row 1 plus row 2 becomes row 2. Let's do it. Now the first row doesn't change. And 7 becomes 0 by design. Then we have 49/2 minus 24. 49/2 minus 24, it's 1/2. And 7/2 plus 0 is 7/2. That's a 0, so no change, and that's 1. Okay. Closer, but still not there. I think what I want to do is I want to multiply row 2 by 2. And that would give me the one that I need. Then 2. Now, I'm going to get rid of that 7/2. So -7/2 row 2 plus row 1 row 1. One, 0, 0, 1, 7, 2, -49/2 plus 1/2. Got -24 and -7/2. Go. Okay. I'm goofed up. -7. Brain's getting tired from all the arithmetic. -7/2 times 2 is just -7. Sorry about that. Okay. Now, may I point that that was the correct answer? That's the inverse. And that's how you can row reduce it. Okay, I already showed that you could row reduce in a calculator matrix, or you could row reduce in a graphing calculator using matrix functions. So that's one way you can do it well. With 2 by 2, there's a formula that you can use, but this only, it's just a trick. It only works for 2 by 2s, but we use 2 by 2s a lot. And even outside this class, 2 by 2s are really important. Okay. So it turns out that there's a formula for 2 by 2 And most of the time we use 2 by 2s. So I should probably teach you how to do it. So if you have A, B, C, D as your entries for a 2 by 2, here's your inverse formula. 1 over A times D minus B times C. And we switch these and we negate these. Here's your formula. So that can be pretty handy. And I will probably use that going forward today when I'm dealing with a 2 by 2, because it makes a lot easier than row reducing. But row reducing always works. And you can also just use a graphing calculator to row reduce, or an online matrix calculator will also do that. But this formula only works only for 2 by 2. So 3 by 3, 4 by 4, and so on, we're just row reducing. Nothing I can do. All right. And thank you for that save about the 24. My brain's just getting tired. You know how it is. All right, next one, same thing. It's just a 2 by 2. We want to find the inverse. Okay. How about I show you how that formula works? Okay. Last time I did row reducing. Sorry. Let's try the formula. So M inverse would be 1 over 3 times 5 minus 1 times 2. And then swap 5, 3, negate, -1, -2. Okay. No row reducing necessary, just have to memorize the formula. That's 1/13, because 15 minus 2, 5, -1, -2, 3. 5/13, -1/13, -2/13, 3/13. So the formula is a lot easier, but formula is only for 2 by 2. Doesn't help us with 3 by 3 or 4 by 4. But I'll say we use 2 by 2 a lot, even outside of this class. If you move on and you're doing something in science or you're doing something in computer programming, there's a lot of 2 by 2s out there. That could be helpful, that little formula. In fact, it's quite helpful. Okay, so that's how you can do that. This is a 3 by 3. So now I'm going to use, coincidentally, I'm going to use this one as my excuse to show you how to do it in the calculator. Okay? And there's a couple ways we could do it in the calculator as well. Depends on how you are thinking about it. So let me plug this in the calculator and show you. Oh, I need to enter in this matrix. Matrix, edit. I want a 3 by 3. 3, enter in my number. One, 3, 2, 0. Okay, I think I did that. 1, -1, 0, 2, -1, 3, 2, 0. Home screen. I wanted to do a little matrix. Second matrix. Click on A here. You remember that notation I talked about with the exponent to be the -1? That's exactly what I'm going to do here. Exponent -1. What are you talking about? Matrix to the first. Oh, no lie. It looks like the TI-83 can't do this. The TI-84 did it. Sorry, I was, looks like the 83 does it. We can do it another way. Sorry about that. All right, so learning on the job here. Is there an inverse? There isn't. We're going to do the reduce row echelon form. Doesn't look like it. Don't see it as a moment. I'm going to edit this. And sorry for the confusion. I thought the 83. So I'm going to change this. This was a 3x3. I'm going to make it a 3x6. I'm going to put the identity matrix on this. What I'm doing is exactly what we've been doing. So if it row reduces this will give me inverse matrix. Okay. We have one of the newer models that can do that exponent trick, but it looks like the 83 can't, but that's okay. We just enter in a different one. So you can see the matrix it's coming from, inverse there. You can also do this by hand. It's not that challenging to do it by hand. It just takes more time than I have to show it. For instance, you would just go -3 row 1 plus row 3 becomes row 3 and so on. In fact, in my notes, if you take a look at them, you'll probably see I did it by hand. But I should also show how to do it on the calculator. Okay, so that's that. Yes.
It gives you a decimal on here, but then it's asking for a fraction in the answer.
Let me see if I can, there is a way to do it. It just so happens that this one didn't have any decimals, but we can swap for fractions to decimals in the calculator. So I just so happened the inverse didn't do that. Let me go to the home screen. It's the same idea. So let's say you have 0.55. You want to convert that to a fraction. You can click math. And the first one is fraction. And converts that to a reduced fraction. It will do that for, well, at least the TI-84 will do that for me with matrices. Okay. And if we need to, we can take a look. But yeah, you can convert, and I do it as well. You can convert from fractions to decimals. Okay. Now, if it's super long, and I think there was one at the end of the homework, last week's homework, that the decimal was so long that even the calculator couldn't convert it to a fraction, but generally it can. Okay. All right. Now that we've kind of, does it make sense what an inverse matrix is? The idea is that you multiply these together, you get 1, and that's where we're getting division. Okay, that's how we're getting division. So for instance, we have 2x plus 3 equals 7. That's 2x equals 4, x equals 2. Okay, how did I do that last step? I divided both sides by 2, right? Well, how are we going to do this with matrices? If we have ax plus b equals c, well, we know ax C minus B, just subtract. We've defined what subtracting matrices is, but how do you divide? How do you divide matrices? We use the inverse. So we're going to see inverse of A times A. And these will cancel the identity matrix. So that's how we're going to get division, is multiplying the inverse. That's how we do it. Okay. Let's see what's next. This is dead easy. It's just an expansion. We're kind of building towards something here, and this is going to expand us to go from a system of equations to matrix algebra. So notice we have 3 equations, 3 unknowns, and we're asked to convert this system of equations to something like AX equals B. Okay, where A is like a coefficient matrix, X is where the variables are, and B is like the solution. Okay, well, it's just as easy as looking at the coefficients. Like, look, that's just the number 1, so that's the number 1. -2, -2, 5, 5. Okay, so I claim that's the same. That you can just multiply 1, -2, 5, -2, 4, 0, 1, 1, 7, x1, x2, x3, -5, 1, 4. I claim that's the same. If you multiply this out, you'll just get the original system of equations. Nothing too crazy about that, right? But we're building towards something. We're going to build towards a general idea of this. Now, one thing that makes me nervous is I can't remember how I entered this thing. Let me check. Okay. It looks like I have to hit the matrix button again for this one. Okay, let me do that really quick. So for this one, I have to hit the matrix button, and I have to know what size matrix I want. Looks like I want a 3 by 3. Okay, now I can just enter in my matrix here. This, I want another matrix, this matrix, 3 by 1. It even shows me a nice little picture there, so I know what I'm looking at. -4, 1, -5. So I did have to enter that in. Good job for that. Now you know. Okay, this one, number 8, is just matrix multiplication. That's the same as we've done before. Row times column, and so on. You can also do that in your graphing calculator as well. You can do that in your graphing calculator as well. I've shown it today by hand, but you can just do it in your calculator. Let me think about this one. Okay, this one's going to be a little tricky. We should talk about this one. We have kind of the reverse here. Kind of the reverse. So here it wants us to solve for the variables. We haven't done anything like this. I'm going to call this A, capital X, capital B, so I can refer to them in our discussion. I want to solve for X, which is a vector. I want to solve for that. How do I do that? Well, if this was 2x equals 4, what would I do? I just divide both sides by 2. Equals 2. It's easy stuff. Now, would you believe me that you could also write it this way? we would want to in algebra class. It is technically right. 2 inverse is just a half. And this would reduce. Okay, these reduce to 1. So we would solve this for x equals 1/2 times 4 equals 2. That's the same thing, elementary linear algebra, or elementary algebra there. We wouldn't write it like that in middle school, but you could have. And now we're going to use this idea to solve our matrix equation, okay? Are there any questions, comments, concerns, or criticisms or complaints about what I did here with just basic algebra? Does it make sense what I'm trying to connect? 2 inverse is really just a half, and that would reduce to 1. Any questions about that? This is how I'm going to solve it with matrices. So my idea is that we have A, X equals B. And the truth is, the order in which we multiply things with matrices matters. It doesn't matter with just numbers because they're one-dimensional, but when we're dealing with multiple dimensions, order matters. So how are we going to get rid of this A on the left-hand side? How do we get rid of that? How do we get this over here? I can't divide a matrix. We don't know what that means. But what I can do is I can multiply both sides by its inverse. Multiply both sides by its inverse. And what happens is this just goes to the identity matrix. It just goes to the identity matrix. So then we've solved for x, just like we did in middle school. So we get x equals A inverse times B. Okay. So that's how I'm going to do. Now I actually have to do it. Get rid of this stuff. So what is the inverse of that matrix? I notice it's a 2 by 2, and I'm going to use that to my advantage. So A inverse equals 1 over 5 times -4 minus 1 times 2. Switch order 4, 5. Negate -1, -2. Okay. So that's -20 minus 2. I guess that's -22. Hopefully I didn't make a mistake. Let me double check just in case. 5 times -4 minus 2 is -22. Yeah, so we got -1/22. Okay. 4 over 22. This is 2/11. 1/22. 1/11. -5/22. So far, so good. Now we need to multiply that times B. X equals A inverse times B. 2/11. 1/22. 1/11. -5/22 times B, -8 minus 34. Row times column. Row times column.
Okay, you lost me. Clear back up
Clear
at
back?
when
Where?
you did the fraction, like I get the where you're doing the inverse formula, but then where are you getting the right next to it with the -4, -1, -2, and 5? Where did that order come from?
This part?
Yeah,
So that came from this, and that came from that formula I showed earlier.
okay.
So that came from, if you have A, B, C, D, the inverse of this is 1 over AD, BC, DA, -B, -C.
Okay.
That's where I got it. Thank you. Now I want to, was that the question? Did I answer the question? Did they get it?
Yeah, that makes sense. I just forgot about the second part of the equation.
Yeah, I don't know if I said it. Probably not. All right, now let's do it. So we got 2/11 times -8 minus 3 over 22. 3. And then what's that? Second row, column, 111 times -8 plus 34 times 5/22. I got 7. No. So that's how I did it. But order matters with multiplication. So it would not have been true. Let's go brown. Not true. I couldn't go B times A inverse. That's not the same thing. It's not the same thing. So order matters with these things. I know students hate it when I show things that are not true. I don't like that, so I'll take that away. I've gotten many complaints about that, me showing things that don't work, but that's the idea. So order matters. Any other questions? This is similar. There's one extra step, but it's pretty similar. I'm gonna label them just so I can talk about them. If you'd let me, I'm gonna call this A, capital X. I'll call this C, and I'll call that B, just so I can explain what piece goes where. I want to solve for that X. The idea. I want to solve for X. All right, so how do I do that? So that's A X plus C equals B. Well, what if these were just numbers? Like you had 2x plus 4 equals 8. Right? What would you do? You subtract 4 on both sides. Divide both sides by 2. But we're doing that with matrices now. So you can imagine it's quite a bit more confusing. So this is just with real numbers, but now we're going to do it with matrices. So I'll subtract C to both sides. AX equals B minus C. Now I want to divide both sides by A. we know that doesn't exist with matrices. So I have to multiply both sides by the inverse. And that reduces to 1, or the identity matrix, just like dividing both sides by 2 reduced to 1. Okay. So now I have a plan of attack. X equals A inverse B minus C. Okay, so that's what I need to do. Now I need to do it. Okay, so what is A inverse? No, here's my A. So A inverse equals 1 times -1 minus 3 times 3. -1, 1, -3, -3. Okay, and that is -1 minus 9, so that's 1/10. And that's -1/10. Okay. So we get 1/10, 3/10, 3/10, -1/10. That's A inverse. What is B minus C? B minus C. I got 20 15. -3 -29 minus -3 would be +3, -26. -15 minus 3, -18. Almost done. Now I need to multiply. X equals A inverse times B minus C. Go. Go get -8 and -6. I want to stress, of course, you can do the arithmetic for the matrix part in the calculator. You can do that in the calculator if you want. No problem. But order matters. Order matters, okay? So going A inverse times this is not the same thing as B minus C times A inverse. You have to do the order correctly. You have to do it correctly. You have to do it in order. And that's going to take more than the past 5 minutes to understand what that means. It took me maybe a couple years to really grasp why that would be true. But please, please, please keep in mind when you're doing the homework, order matters. Keep thinking that. Review this. Okay, you want to keep reviewing. You have to do it in order. That's the idea. That's the idea. So that's how we've developed a way to divide by matrices. And that was a 2x2, so I used the formula. You can also do row reducing by hand or row reducing by calculator. And you can add and subtract and multiply using the calculator as well. Okay. I can't remember what word. We just did number 10. I think number 11 is just, this is pretty much the same thing. Number 11 is pretty much the same problem, different numbers. But it is pretty much the same process as the previous problem. So for time's sake, I'm going to skip to 12. Talk about this. That doesn't mean that this one's harder. It's just different. Yes.
Quick question for 11, does the minus sign in between the two just mean that the numbers will be negative when you put it in?
You're gonna add. We're just gonna add. So this is AX. I'm gonna call that C. I'll call that B. So that means that AX minus C equals B. I can add C to both sides. And then I can do my inverse as I did before. A inverse B plus C. I'll save a picture of that. Other than that, if the first one made sense, that one makes sense. I did it by hand, so you can certainly do it by hand. It wasn't that bad for it. I want to show the other ones just because they're different. Well, so this is a little bit more general. What if the solution changed? And believe it or not, with applications, that's exactly what happens. Your coefficients are the same, but your solution is different. And so we need a way of doing that. Okay, so think of it this way. Of course, we have our augmented matrix, so you can go right back to week 1 techniques and solve this if you like. You can do it that way, augmented matrix, just like we did in week 1. Or our new style is to have a coefficient matrix. Variable vector. Then we have our solution. And they're giving me different solutions. So they're saying, what if K1 and K2 equal this? What if it equaled this? What if it equaled that? Okay, well, if we come up with our inverse, we can solve for it with whatever they give us. Okay, that's the idea. So if this is A, this is capital X, and I'll call that capital K. Well, I can solve for any X that they give me with K by saying X equals A inverse times K. So from there, I have to find the inverse, as you might imagine. This is 2 by 2, as luck would have it. So let's do that. 1 over -1 times -4 minus -3 times -1. 1, negate, go. All right, that's 4 minus 3, that's just 1. Okay. Well, my inverse -4, 3, 1, 1. Yeah. Just need to multiply it by the K's they give. This one, they're giving me -3, -5. So I need to multiply my inverse times that. Order matters. Please be careful of that. In this one, they switch the K's, same inverse. Different solution. This one, inverse. Different solution. Did that. Okay, so that's the idea. You can switch these solutions, do that. And of course, you can do that in your calculator as well. You can have it multiply that, but those aren't so bad. 2 by 2, 2 by 1, are fairly easy to do by hand. But that's the idea. Okay, that's the idea. So that again, that was a 2 by 2 matrix where I need to find the inverse, and I find the formula to be very helpful. With that, remember, you have A, B, C, D. With the inverse of this, 1 over is AB minus. I should remember that it is AD BC. That's the inverse one. Now that the word problem framed, I think I got about 13 minutes to go. I know I'm going fast, but I'm trying to show as many examples as I can for the week. So I know I'm going fast, but it's also being recorded. Okay, this is pretty much the same thing as what I just did. Okay, except it's 3 by 3. So I would use a calculator to do this. I don't have to. In fact, I think I did it by hand. But to show this, I would do it by a calculator. You just have to note that you're going to make your coefficient matrix -1, 16, -1, 1, -7, 0, 0, -10, 1, x1, x2, x3, a1, a2, a3. And so capital X will equal A inverse times capital A. I'll give you various K's. So you just need to find the inverse of that, just as we did before, which you could do from row reduction, calculator, or, well, that's our only options because that's a 3 by 3. So we don't have a formula for that. $11 minutes to go. Let's look at this. This one's just a general idea. The matrix equation is not solved correctly. Explain the mistake and find the correct solution. Assume that the indicated inverse exists. XA equals B. All right, I'll just start. XA equals B. I'm trying to solve for X. Well, what would I have to do? Order matters. So I would have to go A times A inverse equals B plus A inverse. So what I'm doing is I'm multiplying it in the same order. I'm trying to get rid of A, so it has to be the same order. So this reduces to the identity matrix. And I get X equals B A inverse. So I agree, this is not correct. All right, so I wrote that they mix the left multiplication property with the right multiplication property. Order matters with matrices. It's not the same thing multiplying either way. They're not commutative. Okay, so order matters. You gotta watch out for that. That's 14. Okay. 15, similar, says AX equals BA. And we're trying to solve for X. Okay, what I would do is I would go A inverse times A times X, A inverse times B times A. That would get the identity matrix, or those normal algebra that would turn into number 1. So we get X equals A inverse times B times A. Okay. What did they get? They got a solution of X equals B, which is not correct. Okay, what was the mistake? Well, I say that the expression A inverse times B times A does not simplify to B. That's all coming from order matters when you multiply these things. Order matters. 8 minutes to go. Tickets. Concert hall has 9,000 seats in 2 categories of ticket prices, $31 and $41. Assume that all seats in each category can be sold. Okay. First part's really kind of easy, and then I think the last part, it kind of confused me, so I'll go over it. So what can we say? Well, we remember our jazz tickets from last week? It's kind of that all over again. So you'd have something like A plus B equals 9,000. And then you'd have the revenue equation. 31 times A, 41 times B. And this concert, here you go. 2 equations, 2 unknowns. You can solve this in all the different ways that we've gone over. Substitution, elimination method, matrices, inverses, however you like. All those different ways. That's for concert 1. Okay, so for concert 1, that's what I did. Solved. So that's just like week 1. Week 2, a little bit different. The only thing that's going to change is this number. So the only thing that changes is that number. So we still have A plus B equals 9,000, 31A, 41B. And this time, 32. Second concert. Okay. Solve for how many tickets are sold. And so that's what I did. We can use all the various techniques. The technique of your choice to solve that. And then the third one is pretty much the same. So I have A, B, 1,000, 31A, 41B. And in this concert, they have a there. Solve for that, solve for those tickets. Okay. That's pretty much just 3 different problems from week 1 that you can solve. You can use the inverse technique that we just learned, or you can go all the way back to substitution for that. You can use any technique you like. But what is confusing, what confused me for a second, was where these possible outcomes were. So just note that if they sold all of 31, what that would be. If they sold all of 41, which I assume it randomizes with our homework. It's going to be different for each of us. But if it sold all of 31, note what happens there. So 9,000 times 31. And then what happens if you sell all of the 41? What happens there, or whatever yours happens to be? What happens there? So is it possible to bring in a return of 190,000 when all seats are sold? I would say no, it's not, because that's actually less than 9,000 times 31. So that would be the minimum if all seats are sold. The minimum of all seats being sold is 31 times all the seats. The maximum would be all the seats at the $41 mark. Okay, that's the maximum. Going down here. Down. It says, is it possible to bring in this amount? I say no, because that's greater than the possible. For mine concert hall, I have 9,000 seats. So 9,000 times 41, what they're suggesting is more than the max. And then the part C, which I thought was kind of confusing, describe all possible returns and choose the correct answer. So with my numbers, it's 31 times all of the seats and 41 times all of the seats. What did I get? Yeah. That's the maximum and the minimum. Okay, that's all that can happen. So here's the minimum. Here's the maximum. And the difference between the two prices is $10. So I claim from the minimum to the max in steps of 10 would be the range of the prices. Okay, be the range of the prices. That's the end. I always try to show the word problem. And that's the last one for this week. Okay, this week we have, you guessed it, 2 homework assignments, 2 quizzes, just like last time. Please be sure you can get that through the Ivy Plus bookshelf as you've been doing. Well, student view. Two assignments and 2 quizzes, just like last time. I think you can take the quiz up to 3 times. I'm almost certain that's true. And then I will post this lecture and these lecture notes later. I know I'm going a little fast, but trying to show as many examples as I possibly can, so you can refer to that, because we only meet once. Trying to get as much in as possible. If you get stuck on a problem, email me. Yeah. So I will see you next week. So, I think we talked about the dreaded influx method. I think it's next week. Yeah. So there you go. I wish you well again. Just email me if you have any questions. Okay. So I'll see you next week.
Thank you.